Hi there everyone, welcome back to the channel. I'm the GCSE science teacher. In today's video, we're going to be learning about magnetism. And this is a really cool topic at GCSE Physics because it builds on some of the ideas from other topics such as electricity and forces. So I hope you do enjoy this one. If you do, please let me know by giving the video a thumbs up. Feel free to share this video with someone else if you know they would like more help with GCSE science. And of course, if you would like to join this wonderful community we have growing here on YouTube by simply subscribing and clicking the bell so you get notified of new uploads from myself. And thank you so much if you have already done that. I do appreciate all of your support. It's wonderful to have you here. So let's get started, and thank you very much again. So first of all, let's talk about this idea of the word magnet and what a magnet actually is, because often we think of magnets just in everyday objects. We see them on our fridge, we may have them on our bags, we may even have them on some of the clothing or jewelry that we wear. Magnets are really useful objects, and essentially a magnet is a material or an object that produces a magnetic field that can attract other magnetic materials to it. Now, it's really important I state a misconception that often comes up at GCSE. Lots of the time students will say magnets stick together. It's really important we don't use that word because they don't stick together. There's no glue involved here. What we're talking about is a force of attraction, and this is a non-contact force. So we want to start using our ideas of forces in this sort of topic as well, because that's where you're going to get the marks. There's also a force of repulsion, or to repel, and that's when you have two poles of a magnet that are the same, and I'll come on to this in a second. But before I do, what actually is a magnetic field? A magnetic field essentially is the area around a magnet that the magnet has produced, and it has the ability to affect the other objects around it that are magnetic. And essentially the forces of attraction or repulsion are felt or observed or exerted in this area. So that's what it is. Now, we can't see magnetic fields. However, we can see the effects of them. We can also plot them by using compasses. And we actually know of these magnetic fields because the Earth is a great example of where we see the North and South Pole, right? In the core of the Earth, we have an iron core, which is one of the magnetic materials. And because of that, we have the North and South Pole. And that's why magnets work on Earth. But without this, we wouldn't be able to actually have magnetic materials work the way they do. So it's pretty cool. And we also do see the effects of magnetic fields in the case of the Northern Lights or the Aurora Borealis, or even the Southern Lights, the Aurora Australis. If you're interested in any of this that I'm talking about, you maybe have heard of these things, I will link some information for you guys below because there are some really cool things that magnets are able to do. We can see them in different ways. So I'll link that for you guys. But anyway, when we look at a magnet, you really do need to know of two key things. We need to know that there are magnetic materials that will essentially attract to magnets. So we have iron, like I mentioned, and we have steel. Steel is actually what we call a ferrous metal because it's an alloy. Essentially, that means it's made up of a mixture of metals. One of those metals is iron, which is why steel is magnetic. We also have cobalt and nickel. So those are the four magnetic materials that you need to know about. A magnet itself has two poles. So these are the ends of a magnet. So we have the North Pole and the South Pole of a bar magnet, which you see here. Now, in the case of magnets, we have this idea of a repulsion or an attractive force. So when those two poles are placed together, let's say we've got south and south, you can see that those poles don't actually want to attract, they actually repel. Now, if you've ever held two magnets together and you've tried to feel that repulsion force, you'll actually be able to feel that. So I do urge you, if you do have any magnets, try and see this if you can, because it's a very cool thing to feel and observe. And the same with the North Poles. If you have two North Poles facing, they will also repel. And you can see I've just drawn the field lines to show that repulsion there for those ones. We also have attractive forces. So if we have a north and a south facing together, they will attract together. Remember, we never say they stick together. We want to say they attract. And then lastly, magnetism in general, we want to think of in terms of like a vector quantity because it has direction. So magnetism, or the force of attraction, which is a vector quantity, remember, it has direction and magnitude. That's why we have arrows drawn in the field lines. But it's very important to know that those field lines will always go from north to south. So that's why I have drawn them like that in this case. So that's a bit of an overview. Let's talk about other types of magnets and if there are any differences. So a permanent magnet, as the word would suggest, is a magnet that is always magnetic. And this is what we think of when we think of things like a bar magnet or a horseshoe magnet. And it's because these are able to produce their own magnetic field all the time. So the magnetic field cannot be turned off or on. It's just always like that. So it will always be able to attract and repel other magnets, depending on which way the poles are facing. They'll also be able to attract other magnetic materials as well. In the case, though, of an induced magnet, this is actually slightly different. So we can get magnetic materials to act as a magnet if they're placed inside a magnetic field of a permanent magnet itself. So let me give you this example. We have our bar magnet, which you can see here, and all I've got is some steel paper clips. And the first paper clip at the top, you can see, is in the magnetic field of that bar magnet, that permanent magnet. Now, on its own, that steel paper clip is not magnetic. We can't use it as a magnet. But if we were to place it in the magnetic field of a permanent magnet, it actually starts to be induced as a magnet. magnet. So it has the ability to actually attract other magnetic materials, which is exactly what's happening below it. You can see we've got that steel paperclip. That second one is attracted to the first one because of that magnetic field that's associated with the first one. So the key idea here is to know that if we were to place one of those induced magnets next to another magnetic material, it can attract those other magnetic materials. However, it does not repel. And that's the key bit they want you to know for the exam, that induced magnets do not repel, but permanent magnets do. Another thing to mention as well is that when the magnetic field is essentially removed from that induced magnet, the induced magnet loses its ability to attract those magnetic materials, and the magnetism is lost quite quickly. So that's another key idea for you guys to know. Also, a bit of a story here. If you've ever had those fridge magnets on your fridge and you've got loads and loads of paper held up by one tiny little fridge magnet, you'll notice that actually it often falls off. The paper won't be able to stay to the fridge, and that's because magnets work very well as close to the magnetic material as possible. So the increase in distance means the weaker that force of attraction, and that actually makes a lot of sense because essentially the further you get away from it, the further you get distance from that pole of that magnet, the less force of attraction. So it's really key to know that in a permanent magnet, the forces are most concentrated at the poles. But as we increase that distance, the force starts to decrease. So that's just a one way to remember it. If you have loads of paper on your fridge and it keeps falling off because you've got one tiny magnet, it's because there's too much paper from the magnet and the metallic material in the fridge, and that's probably why that's happening. So like I said, you can't actually see magnetic fields, but we can definitely plot them to discover what the shape of it is. Now, in the case of a bar magnet, you'll be expected to write a method for how you would plot a magnetic field around a bar magnet. And what you essentially need is a piece of paper, a bar magnet, of course, and a pencil. You'll also need a plotting compass. And the compass essentially helps us navigate around the bar magnet and see where those magnetic field lines are moving, but also where they are located as well. Now, the image you see here is a typical shape of a magnetic field line around a bar magnet, but of course I've only drawn a few lines. One thing to mention about my image is this is like a rough sketch, but if I was to do this more accurately, I would of course draw a few more lines than this. I would also make sure that my arrows were really clear, and you can see that they're going from the north to south pole, but we can actually prove that that is the case. So what you'd need to do, the first thing you'd need to do in the method is to put a compass next to a bar magnet, and I would start off at the north pole side. And what you'll see is the compass is on a bit of a pivot. So a compass itself works pretty much like a bar magnet. It essentially contains a small bar magnet on a pivot, so the needle will actually rotate. And that's what we're looking for. We're looking for that direction, and we're following that direction until we go from one pole to the other. And you'll see that it makes this kind of shape. The compass needle as well, by the way, simply just follows the direction of the magnetic field. It also works for the Earth's magnetic field as well, which is why compasses, they are often used to help with navigation. Of course, we don't really use this nowadays because we have things like Google Maps, but if you even go on your phone, you'll see there is a compass on your phone still, which is pretty cool. But that's how it works. It essentially tries to track the magnetic field lines of the Earth. Now, one thing to mention as well here before we get into the method is make sure your magnetic field lines, when you draw them, they do not cross, because they never do. They're actually spaced out, even at the poles, which is where the highly concentrated force is. Those field lines do not cross. Okay, so let's talk about the first thing. First, number one you want to do is to put the compass next to the pole, let's say the North Pole. You want to draw a dot next to the compass needle where it is pointing to. You then want to move the compass on top of that dot and draw another dot to where the needle now points. You want to repeat this until you reach the other side of the magnet, which will eventually happen. So you'll go out in a bit of a curve and come back round from north to south. You want to repeat this whole process at different positions around the bar magnet. You might even want to start somewhere in the middle, somewhere towards the end of the pole, and that way you get a big variety of different lines that you essentially want to draw. And this is what we're doing, is we're mapping out that magnetic field. Once you've done this and you've got a few different lines like you have here, you simply want to connect those dots in a nice smooth line using that pencil. And then you want to draw your arrows on. So it should point from north to south. And there you have it. You've got your magnetic field lines drawn. Another way we can show magnetic field lines between bar magnets is actually using something called iron filings. Essentially, this is just really tiny bits of iron that have been broken up, and they are essentially in this like powdery form. And what we can do is we can place it next to a bar magnet. And as you can see in these two images, you'll be able to see those nice field lines. Now, often this is done as a demonstration. We wouldn't really be able to plot the magnetic field lines as accurately as we would with, say, a compass. And also this is really difficult to remove as well. So this often isn't really done. But yeah, the one that you do need to focus on is the method for a compass and a bar magnet, and using that to plot those magnetic field lines. The one thing I will say about this, although the magnetic field lines are quite clear in the first image, the second one you can see that there does appear to be a bit of an overlap. Now, please don't get into that misconception that magnetic field lines will actually cross, because the the iron filings are showing a bit of a messier structure, the magnetic field lines are never going to cross. They're always nicely spaced out, even at the poles. So that's one of the misconceptions that can be led with this particular version of the practical. So just be aware of that. At the poles, it does look like a big clump of those iron filings at the poles, like I said, but they are in reality, if we do use a compass, you'll be able to see that those magnetic field lines are separate, so they never cross. So as a bit of a bonus for you guys, I wanted to show you this magic trick, which I think you'll enjoy. So if you do enjoy science as much as I do, you will love the fact that there is a lot of magic with science as well. So we can do something called a floating magnet experiment. And I'd like you to try this if you can, if you've got a magnet and some paper clips, a bit of sellotape, a bit of string. This is a really cool thing to show other people. And then you can explain the science behind it. It's just a lot of fun. So let me know in the comment section if you try this and you get any good reactions, because often when I show students this in real life, they absolutely love it. And often think that I'm, a magician or something, which is funny. But anyway, what you have to do is you simply get your magnet and your paper clip, and because of that attractive force, they will attract together. But because it's a non-contact force, you can actually essentially have a floating object. And you can see the equipment set up here. That floating object is essentially being held together by that magnetic force. So it's really cool. Try it out and let me know how you get on. And that's it from me today. I've been the GCSE science teacher and you have been curious. If you did enjoy this video, feel free to give it a thumbs up. Please do share it with someone else if you think it will help them. And also do subscribe, because we're so close to hitting 1,000 subscribers here on my YouTube, which is an incredible milestone, but also a mind-boggling thing as well. It's wonderful to have so many of you in this wonderful community. So thank you so much for your support. If you do have any questions or queries about any of the GCSE content I've covered, or you'd like maybe to make a video request, feel free to do that as well. It's always good to hear from you guys. But in the meantime, have a fantastic day and I'll catch you in the next one. Take care.